So this video, oh dang, I said I didn't start the video by saying all right. Oh dang. Okay, well, hopefully this is a good take then. So this video is going to cover gauge R&R. Effectively, let's say, again, you're cutting a beam into a smaller beam. You're never going to, the length of this beam is never going to be perfect. It's never going to be the exact length that you want. There's always going to be some variation. Now that variation can come from, in GR&R, there's three different factors that it could come from. It could come from part to part variability. It can come from repeatability, and it can come from, it's R, repeatability. The last one is reproducibility. Okay, so let's define what these three variances are, or variations are. So let's start with part to part. This is basically just the variance associated with the manufacturing process. Like, even if the operators do everything perfectly, even if it's all robot controlled, and there's no operators, there's still going to be some variation. And this is the term that accounts for that. What do I even want to say for this? Part to part. With the machine. I think with the machine is right. Part to part is variation associated with the machine itself. Okay. Reproducibility. Is how well the same operator can measure the same part with the same tools and get the same result. Even if you measure something like 5 times with if you measure the same thing 5 times with the exact same ruler, you probably won't get the exact same result every single time. So this accounts for that. So let me write that out. I'm going to reorganize this, and you're going to stay with me while I do it. Okay, so how well the same operator can measure the same part with the same tools and get the same result. If repeatability is causing high variation or variance, then you probably want to retrain the operators. The last thing is reproducibility, which is how well multiple operators with multiple measurement devices measure the same part and get the same result. So like if you have 2 different operators at 2 different measuring stations, and you give one of them a part, then you give the same part to the other operator, they're not going to get the exact same measurements. So reproducibility accounts for that sort of variation. Phone's buzzing. Hopefully the world didn't blow up. I'm not going to look now. How well... Oh. How will multiple operators with multiple measurement devices measure the same part and get the same result? Okay, so those are our definitions. That probably took half the video. So now, what do you actually need to do the study? What are the results? What do the results tell you? So, okay, still need my textbook. Let's look at this. So to do the study, you need a couple different things. So you need a couple parts. Let's say you have 3 parts. Part 1, I'm just going to call it 1, 2, 3. I'm going to move the third one down a bit further. You need a couple different parts. You need, I'm gonna move that line over here. You need the operators to do a couple different measurements. So let's say M1, M2, M3. This might be a little confusing, but I'm just going to write this out here for me. So you need multiple different parts. You need each operator. So let's say you have operator A, B, and C. A, B, C, C. Okay, so you need each operator. Well, let's start with, what does this mean? You need each operator to measure the same part multiple times. You need multiple operators to measure the same part as well. And you need Okay. So the part to part is measured by looking at, well, because you have multiple parts. So you're going to see, on average, how different are the parts. Repeatability, how well the same operator can measure the same part with the same tools and get the same result. I messed this part up. You don't need this. Oh, dang it. You don't need that part of the table. Okay. Cool. So part to part, you have multiple parts. Repeatability, how well the same operator can measure the same part with the same tools and get the same result. This operator has measured part 1 3 times, measures part 2 3 times, and measures part 3 3 times. So you have multiple instances where you can see how well the operator, like how close is this number to this number to that number, or how close this number is to that number is to that number, etc. The math behind this, I didn't do a deep dive into the math behind this. I kind of just throw these numbers into a program. But I don't think it's that complicated. Okay, and then reproducibility, how well multiple operators with multiple measurement devices measure the same part and get the same result. So you have three different operators. Well, you have three different operators all measuring the same part. So you can compare those to get that variation. So this is the type of data you need to be able to get numbers for part-to-part repeatability and reproducibility. So you can throw these, once you have this Excel table, you can throw it into, I use Minitab and JMP before. I've used those two, but I'm sure there's others. You could throw this into Minitab or JMP and it spits out, for example, let's say you get a repeatability of 53%. You get a reproducibility of 78%. And you get a part-to-part variation of 32%. Okay, when it spits out numbers, it'll spit out a lot more numbers than this. So you want to look for the percent study var. You want to look for that section, percent study var. All right, so what do these numbers mean and what do they tell us? So this is telling, well, before I even go into the math, this is telling us that most of the variability is coming from reproducibility. So this is saying that different operators are using different measurement tools and they're measuring the same part, but they're getting different results. So in this case, you'd want to look into the tools, like the measurement tools that the operators are using, making sure that the tool on table 1 measures the same as the tool on table 2. The second highest is repeatability, which is how well the same, repeatability. How the same operator can measure the same part with the same tools and get the same result. So in this case, if you wanted to improve this number, lower it, you would either retrain the operators or also ensure that the measurement, you could look into the measurement tool, but typically you'd retrain the operators or ask them to show you how they're measuring it. Part to part, this is the best variation in the whole study. This is saying, well, this isn't good. Ideally, you want part to part to be like in 90% of the variability. You want part to part to account for almost all the variability. You want the operators and the measurement tools to be as consistent as possible. Greater than 90%. In this case, it's 32%, which is way lower than 90%. So if you're lower than 90%, typically you want to try to reduce repeatability and reproducibility by doing the things I mentioned before, like double checking how the operators are measuring stuff, and double checking the measurement tools that the operators are using. Okay, so what does kind of the math for this look like? So I'm going to draw a triangle. And this will be total variation. So by default, that is 100%. And then I'm going to draw part to part. You know what? I'm going to redraw this to make it look more like what this is going to actually end up looking like. %. Then you have part to part. And then you have, this is called gauge R&R variation. I don't know why they call it that, because the whole study is called gauge R&R, but that's what they call this side. So in this case, total variation is always 100% because it's total. Part to part, we got 32%. So that means that if we do the math, where we have a squared plus b squared equals c squared, Pythagorean theorem, we get that GR&R variation should be around 94%. 94%. Cool. Where am I going with this? So this side also has a triangle. Yeah, it'll probably look something similar to that in this case. With repeatability, and reproducibility. Reproducibility, what did we get? 78%. So maybe this side will be a bit longer on that side, but you get the idea. 78% and 53%. Cool. And if you do the Pythagorean theorem for this triangle, you'll get 53 squared plus 78 squared equals 94 squared. So it works out here. And then if you do it again for this triangle, you'll get that 32 squared plus 94 squared equals, I got 99.3, but that's basically 100%. So it's close enough. But that is the triangle that they use for this stuff. The big part of this whole thing is to understand these definitions, understand the result, and understand that ideally you want part to part to account for 90% of your variation. You want very accurate measuring tools, and you want very consistent operators. If part to part is if your variation is too high and part to part is like 90% of your variation, you want to improve the part to part. And ways you could improve the part to part would be just buying more accurate tools, kind of. That's kind of the only way. Effectively, this is how to do a gauge R&R study. Cool beans.